So hello everyone and welcome back to this next lecture in the DC to DC video series, and in this lecture I'm going to continue with the ZETA converter. So this is where we had left off in the previous lecture, where we had added the ZETA converter circuit schematic, which is this one. We had compared it with CHUK and the SEPIC converter, and we had looked at how the ZETA converter differs from the CHUK and the SEPIC converter in terms of conduction and how it operates. However, this is only theoretical. So to continue with this, I'm going to now edit the circuit parameters of the ZETA converter. But before that, as always, a little bit of background that if you are interested in these kind of video lectures but would like something a little more comprehensive, that is a complete online course, I do have complete online courses on the MOOC website Udemy, and this is one of them. This is simulating power electronic circuits using Python. In this, I talk about how you can install Python power electronics, a little bit of basic theory about power electronics, and finally we end up simulating a buck converter as a test case. Right. Now, if you are interested more on the signal processing and the control side, I have another course which is also on Udemy, and that is called Basics of Digital Signal Processing for Power Engineers. And in this one, I talk about signal processing using Python. So I talk about the signal package in SciPy for using the filtered frequency response analysis, as well as using it to design filters. And as a test case, we design a low pass filter and a band pass filter. So the last one, and this is the latest one, is simulation of magnetics for power electronics using Python. In this one, I talk about how we can simulate a transformer with Python, and I talk about different types of transformers, a multi-winding transformer, and finally there is a test case of a flyback converter which has a multi-winding transformer and is also a high frequency transformer. So these are the courses which I have available. The links for the courses are provided in the description for this video. So with this, I'll get back to the lecture. So now that we have added the circuit schematic, and if we process the circuit schematic, we find that there is no error. This is where we had left off. So it says the circuit does not have any detectable errors, so that means we are good to go. So we can go to the next stage, and that is edit circuit parameters. So in edit circuit parameters, we have only one file. We can just go click on view components, and here we have the parameters of all of them. So let's quickly go through this. So the first one, ammeter C1. Let's go over. This is ammeter C1. Now this is just a decoupling capacitor, so you can actually choose any one, any direction, because the current through the decoupling capacitor will reverse. When it is charging, it will flow towards the right. When it is discharging, it will flow towards the left. So let's just choose it towards the right. So it is positive direction is 1M, which is to the left. Let's change this and make it to the right. You could leave it here as well, but just to keep it compatible with the previous simulations of the CHUK converter and the SEPIC converter, I'll make it to the right as well. Then finally the ammeter Cout. Let's go all the way here. That is the ammeter Cout. This is the current in the output capacitor. In the ZETA converter, the polarity of the output is the same as the input. So which means the output has a positive polarity towards the upper terminal, right? So therefore the current flows downwards. So which means that the positive direction of the current has to be downwards. So let's go and change that. So this should be 12 AA because it is currently 10 AA. And finally there is ammeter D1. This is a fairly important one. Let's go. That is this one. In the ZETA converter, the diode has a cathode which is pointing upwards. That is, the polarity of the cathode is upwards. The current through this diode flows in the upward direction. That means the positive polarity of the ammeter D1 should be upwards. So let's go and have a look. It is upwards, so we can leave it as it is. Then finally there is ammeter L1. Let's go have a look. This is ammeter L1. When the switch is turned on, the current flows in the clockwise direction, therefore the current flows downwards. So therefore the positive polarity of ammeter L1 is downwards. And it is upwards, so let's reverse that. 13F. And its next one is ammeter L2. Let's go all the way here. The ammeter L2, the current flows towards the right because when the switch is turned on, current flows through the inductor, and also current flows in the forward path when flows through the output capacitor. So therefore the positive direction of this ammeter is towards the right. It is here towards the left, right? So let's change it to the right. It is 1x. And then there is ammeter in. This should be towards the right because it's pretty obvious. The current flows towards the clock in the clockwise direction. So this can be, and this is 1B. That's correct. So there is no need to change it. Ammeter load is this one. As said before, the load should always be downwards because the positive polarity of the output is upwards. So we are going to measure the current downwards. So load is currently upwards, the positive polarity. Let's change this to downwards, that is with respect to the component position. And then there is capacitor. We can just make this to be 100 microfarad capacitor. I would encourage you to play around with this value, but it's not really that necessary. The component position is at 1J. The positive polarity is towards the left. That's perfectly okay. Just save the parameters. The positive polarity of the capacitor is actually more for debugging purposes. It's not really a very important parameter. The diode D1. As before, the diode D1 is pointing upwards, which means the cathode of the diode D1 is upwards because the current flows upwards, right? The diode conducts in the upward direction. So the diode positive polarity is upwards and we can leave it as it is. Now, since this is a ZETA converter, we can leave the voltage level to be 120 volts because we are dealing with a 12 volt input, right? So this can be 120 volt. The inductor L1 is at position 4F, it's 1 millihenry. We can leave it as it is. You're welcome to play around with this value. And the same with the inductor, it can be 1 millihenry. It is at this position 1U. It is also okay. The resistor, this resistor C1 is the parasitic resistor of the capacitor. It cannot be 100 ohms, it has to be negligible. So let me just edit this. So 10 milliohm is fairly negligible resistor for a parasitic capacitor or a parasitic resistance of a capacitor. And the same for Cout is also the parasitic resistance of Cout. Just to verify, we can go over and have a look. It is this one. This is the parasitic resistance of this branch because every branch must have some resistance. And keep going. There is resistor L2 and resistor R1. These are also parasitic resistance. Resistor R1, let's see where it is. Resistor R1 is on this branch, and this is also the parasitic resistance of L1. Any parasitic resistance has to be negligible because it is just to give some kind of series resistance to an element like an inductor or capacitor. The load is a series resistance. In that, I suppose we can leave it to be around 10 ohms because if we have a voltage of, well, we can make it around 7 ohms or 8 ohms because if we have a voltage of around 12 volts at the input and we use it in buck and boost mode, then we will end up with a 1 ampere current drawn by the load. So this should be okay. But go ahead, play around with this value. and we come to the switch. The switch is, as always, a very important component. Let's go over to the switch. This is where it is. The switch has to be in such a direction that it conducts towards the right. So when the switch is on, the voltage source charges the inductor and charges the output capacitor and the decoupling capacitor through this forward path. So which means the negative polarity of the switch has to be towards the right. So the negative polarity is towards the right. The voltage level is also correct. The only thing that needs to change is the control tag. We should give it a unique value. So let's edit this. All we need to do is say S1 gate. This is also mainly for debugging purposes, but I would recommend to give every control element a unique tag. And the voltage source. Now the voltage source, as we said, we are going to take it as a DC. So I'm going to make all these 0. The DC offset will be 12 volts. The positive polarity is 7A. Let's have a look. This is the voltage source. We want a positive polarity towards the upward direction, which means that the positive polarity has to be upwards, and that is what it is. So we can leave this as it is, save the parameters. And I believe there should be one more. Now there's the voltmeters. Now the voltmeters, let's come have a look. This is the capacitor, this is the voltmeter. Now we would like to, this capacitor is charged and discharged, but it is mainly charged towards the right, which means we expect a positive polarity towards the left, which means the voltmeter should have a positive polarity towards the left as well. So if you look at this, 5L is the component position, 5K is the positive polarity. And if you look at it, that's exactly what it is. So we can leave it as it is. No need to change it. The voltage level is 120 volts is okay, because we are dealing with a system of 12 volts. So we have a voltage level which is 10 times larger. That's good enough. The component type is, we have last one is voltmeter. Here again, it is the output voltage, which is all the way towards the end. This is measuring the voltage across the load. And it would be good if the positive polarity of this voltmeter is towards the upward direction. So that is what it is. You see the component position is at 8E and the positive polarity is 7E. The voltage level can be 120 volts because we have a 12 volt system. So with this, we are done with the parameters of the ZETA converter. Now, to stop these lectures from getting too long, I am going to end this lecture now. In the next lecture, we will get started with the open loop control, or rather the pulse width modulation, and run the simulation once to see the initial result. So with this, I'm going to end this lecture. If you have any doubts, please do post in the comments or email me or message me on social media, whichever is your preference. Otherwise, I will see you in the next week where we will add the pulse width modulation file for this ZETA converter. So thank you so much for listening and see you next time. Goodbye for now.